Hello everyone. How's everyone doing today? Hope you're doing as well as I am. Today I'd like to review the JFG, the public space debate we had the other day with Peter. And we talked about black holes. And there's a little bit of problems with some of the things that were said. Maybe everything wasn't clarified, and I'd like to kind of clarify those things today. Anyways, first I want to make sure that I cover another subject, which is, Boras, where we have this conference in June, and there's been a little bit of an update, and that's on the 8th of June, Saturday. That's when our conference is going to take place. So that's 8th of June in Borås, Sweden. Okay, it's a little town there, right between somewhere between Copenhagen in Denmark and Stockholm in Sweden. So you can find it on the map. Borås, Boras. The A with the angstrom little sign on it. Okay, Borås. I hope I'm pronouncing that well. I'm sure our host over there is going to correct me on that if, if I don't say it right. Okay. Um, so, what's the deal with black holes or with what we did? Well, let's start with what happened on Sunday. I had a little debate, and it was with Peter again. He's a mathematical physicist. He teaches at a university, and he's primarily a quantum guy. He does research, for what I can tell, in the realm of quantum. He's not specifically geared towards general relativity. So we can excuse him on that count. Not everybody's an expert in every field. Just because someone is a mathematical physicist doesn't mean that he knows all of it. Okay, he does have a general understanding of each of the fields, but he specializes in quantum. And JFG, there you have him, smiling as always, with his French accent. Um, Carries his program called the Public Space. And he brings us every now and then to discuss some of these things. Okay, things such as what we talked about the other day, which is black holes and dark matter. I like to concentrate a little bit on the dark matter side. I'm sorry, on the black hole side, not so much on the dark matter. I think the dark matter essentially is the same thing. And in general terms, my view on this is that both dark matter and black holes are conveniently invisible, conveniently heavy, and they're both just for people so that they know for a fact what's going on. They're just variables in an equation. That's all they are. They represent mass, runaway mass. Lots of mass in a small area, small region, small volume, or no volume in the case of black holes. But the idea is that there's a lot of mass in a very small region. And why did they have to do that? Because that was the only way they could explain some of the phenomena that the astronomers were observing out there. One of them was that stars were going around nothing. They were orbiting a center, and there was nothing in that center. And they were going kind of fast, you know, like several. I measured one of those to be 40. What was it? Yeah, I think it was 45,000 kilometers, and it was doing it in 5.6 days. That's Cygnus X1. And they said, what is this thing orbiting around? And other stars, they noticed that they're losing gas, like their gaseous skin, and it was going into nowhere. They were just losing, something was dragging this gas from the skin of the star, and it was going off into nowhere. So, black hole. Dark matter, same thing. Um, they couldn't figure out why the galaxy rotated as a bicycle wheel, as a carousel wheel, everything at the same time. Or like I like to say, the buggy's on the outside just as fast as the horsey's on the inside. If everything is kind of fluid, then the horses should go first, and the buggy should trail behind as the carousel twirls. Just like Pluto. Pluto falls behind Mercury. Mercury goes around the sun in 88 days, Earth days. And Pluto takes 248 years to go around the sun. So it lags, it falls way behind. That's not the case with stars on the outside of almost any galaxy. Stars on the outside of a galaxy travel just as fast or faster than the ones on the inside. They keep pace, all around as the galaxy goes around. So what it suggests to you is that, the whole galaxy rotates as a wheel, okay? It rotates as a single entity. That's the notion that you got to get from this, okay? We got some. Hi, Pedro. Hello. Let me adjust this thing here. I want to just adjust. Okay. I guess I can't get it to adjust completely. I don't know why. Okay. Anyways, so that's where they got these notions. That's where they've got the notion of the black hole. That's where they got the notion of dark matter. They just had to put a lot of, like I say, a lot of kilograms. They put a lot of kilograms in certain regions to produce the effects that they were observing. They had no other way to explain this except saying, we have runaway mass. So, this is what the issue is. Oh, there we go. The issue is that, they had to invent this variable. In one case, a variable called black hole. In the other one, a variable called dark matter. What's the problem? The general problem, they're both conveniently invisible, and they're conveniently very heavy to satisfy the equations necessary to produce those effects. Well, I do it a little differently. I'm saying that everything's interconnected. And as far as dark matter is concerned, you can see that right away, that if everything is connected, of course, it rotates as a single platform. It rotates like a bicycle wheel, rotates like a carousel, like a merry-go-round, okay? And that's the main point there. But I want to talk about some other, a little, troublesome issue that popped up the other day in the talks with Peter and JFG. JFG came up and he started his show with the following. He started his show with this little picture there, right? The pictures that he started with is the one on the left, the blue ones right there, okay? And so what was the deal? He said, look, the sun weighs down the canvas of space-time, and since it's got somewhat, so much mass, it'll do that little curving in the canvas in the, what is in the fabric. That's where I was in. The fabric of space-time. If you take a neutron star, well, it'll bend it a little more. In other words, it'll take it down further. And if you have a black hole, it'll just, take it all the way down, very pronounced, okay? And his image is the one you find on the internet. Here I have the ones on the right. Those are the ones that I put in there. And you can see that he's pretty much right. That's the way people visualize this thing. You see those cones with flat tops on the two top ones on the right. And then on the bottom, what you see is the famous discovery that two black holes rotate around each other, and they create these gravitational waves. Those gravitational waves were allegedly discovered by a team from LIGO, and a couple years ago, I think February 2016. And what happened? Well, they got a Nobel Prize for discovering that, because they kind of killed two birds with one stone. They found not only that, not found, but they confirmed, or they proved for the second time at least, that there are in fact black holes, because what else could those gravity waves come from except the collision of two black holes like a billion years ago? And they also proved the gravity waves. So they killed two birds with one stone. They showed that black holes exist, because what else could have uh, created those waves except the collision of two black holes? It had to be two massive objects. They didn't see the massive objects. This is an extrapolation. This is an inference. They made the assumption, but they call those things proofs in mathematical physics. They say, we've proven it. We've proven that black holes are there. What else could have caused it? And then they proved the gravity waves, which had been predicted by Einstein, allegedly, right? And first we need to clarify that Einstein did not believe in gravity waves, like he didn't believe in black holes, and he didn't believe in Big Bang, okay? People like to use the word Einstein because they can get their point across. They say, hey, Einstein said so. Oh, if Einstein said so, who's going to criticize it? But here's Einstein's 1918 paper 100 years ago. And this is his, it was printed in a German journal, Über Gravitationswellen, okay? And he had this published in 1918, and in it he argued that gravitational waves are nonsense. He later wrote another I'm not sure he wrote a formal paper, but I think he did, but I'm not so sure about that. About 1935, 1936, about the time he was fighting with the quantum folk, with Niels Bohr, criticizing quantum, saying, God does not play dice, that kind of thing. And he criticized, again, the gravitational waves. He says, no such thing. He didn't believe in gravitational waves. But people today say, oh yeah, thanks to Einstein, we have black holes, we have gravitational waves, we have Big Bang. Einstein didn't believe in any of those. He wrote papers against those ideas. But today they use, Einstein's name to back, on the basis of authority. They use it to back their ideas. Anyways, so gravitational waves, and here you have a GIF that shows the two black holes rotating around each other. They get closer and closer and closer until they collide. When they collide, they generate gravity waves that extend all the way to Earth. Okay, so this is the notion that you're supposed to see these gravity waves that come. They are created from the collision of two black holes, okay? And I think it's pretty straightforward, the illustration there, okay? Okay, so we have these two balls, or holes. They run around each other, they collide, they create waves, waves come all the way to Earth. Straightforward, right? Okay. And Peter presented a scenario which is not identical, and it's a quantum thing. It's got nothing to do with gravity waves or with black holes, but it's got to do with waves, and that's what I want to talk about today. Here's his scenario. He says, look, if you put oil, and he didn't do the experiment, but he just referenced it, and he says, if you put oil in this that blue part of that picture is the oil, and you have a shaker, it shakes that whole contraption, and you'll see that little dot, a little blue dot there. And that little blue dot, jumps on the surface of that blue oil, and you can see the little waves on the surface there, and the blue dot not only goes up and down, jumping on that surface, but it also moves across, and it also does entanglement. In other words, it does what the two black holes just did: run around each other and affect each other from a distance. And this is more or less what it looks like. Okay, here you have the oil drop just moving across the surface, also rolling around each other, called entanglement. You have it jumping on the oil drop jumping on the lake of oil. And all this because they're creating a vibration from underneath, on the tank where the oil is. And they do all these fancy things, and they are able to film this with high-speed cameras so that they can see exactly what's more or less what's happening. Okay, and you can see this resembles in some way, to some degree, what the two black holes did when they. Here, I'll show it one more time. How the black holes rotate. Okay, and they create gravity waves. Well, the oil drops create the waves, which in turn, have a symbiotic relation and affect the oil drops. Okay, straightforward, more or less. Okay, so there is a common a common theme here, and the theme that I want to get to has to do with waves. Okay. And let's see if I can, well, first let me just get rid of the black hole just off the bat so that you are convinced that black holes have no place in science, let alone in physics, okay? Black holes are nonsense, 100% nonsense. And the main reason, here it is, it's the argument I like to start with, that's the black hole has never been defined. No one has any idea what a black hole is. That's the first issue. And specifically, they can't tell you, not a single mathematician on earth can tell you, will ever tell you, because the day they do, their whole theory goes down the drain. They cannot tell you whether a black hole is a black ball or it collapses down to nothing and becomes a region, a hole in space-time. It kind of rips space-time open and becomes a little hole, an entrance to space-time, if you can imagine that. It's kind of surrealistic, but this is what they're trying to convey to you. So the question is whether you can tell the difference between a ball and a hole. And many mathematicians, they went to college, but they skipped kindergarten. So they can't tell the difference between a ball and a hole, and you can't really, put this against them. Not everybody is as fortunate as you and went to kindergarten. But, I would like all the mathematicians to look at this Bugs Bunny picture here. Bugs can tell them what the difference between a hole and a ball is. The hole is into something else, in this case, the ground. And ball is a standalone object that he has in his hands, right? So there's a difference between a ball and a hole. They're both round, but one is round three-dimensionally, the other one is round two-dimensionally. One is an entrance to something else, the other one is a standalone object. And we can go on and on with the differences between them. You'll just have to go to kindergarten to figure out, what the differences are between a ball and a hole. And the mathematicians cannot tell you whether a black hole looks like the guy on the left or the guy on the right. Is it like a ball or is it like a hole? That's the issue. Okay? And hopefully, most people can tell the difference between them, but not everybody can apparently, so what can I say? Okay, so that's the first issue. The other issue is that the black hole is supposed to do this through mass. It's supposed to affect things at a distance through mass. And that's a problem because in the case of, like I just discussed about dark matter, if all the stars are, if all the atoms in the universe are interconnected by ropes, extended ropes, that means all the stars are interconnected by ropes. I have a little GIF to simulate that. And it looks like this. Let's wait till it starts. That's towards the end. All stars are interconnected. That's what I'm showing there. But essentially, if you go away from the sun, you should go from the bird's beak to the linear regime. What is the bird's beak? Well, the bird's beak is that part of the sun where all the ropes are coming out. They form a bird's beak as they go all the way to the nearest star, in this case, Proxima Centauri. And as you approach Proxima Centauri, you also have a bird's beak. So every star has to have a bird's beak when it's connected to any other star. Okay? But anyways, all stars are interconnected. That's the Enterprise trying to leave the bird's beak. It slows down as it goes into the linear regime. Okay? When it goes into that linear regime over there, Newtonian gravity is no longer in effect. Now you go into this linear gravity or non-gravity or drifting gravity, whichever way you want to look at it. Okay? Okay, so that's the first point that I want to make, that all stars are interconnected, and because they're all interconnected, the whole platform called galaxy rotates as a carousel, as a bicycle wheel. End of story. So how do they do it in general relativity? Well, in general relativity, they do it a little differently. See, they do it more or less like JFG showed here. He showed these black holes, and you weigh down the canvas of space-time, the fabric of space-time, and things fall down the hole. Okay, that's how they do it. And so it's done completely with mass, with this thing called mass. And what's the problem with mass? Well, the problem with mass is, first, there's no definition of the word mass. Okay? The general notion that people have out there is that mass is how much matter there is in something. Matter is anything you can touch physically. Okay? Eric Weinstein's World of Physics says the quantity of matter contained in an object. Straightforward. It's what you learn in high school. And Wikipedia has a couple definitions there, both in the same way. One may distinguish conceptually between at least 7 different aspects of mass, right? And one of those is that it's the amount of matter in an object. So they all agree that it's the amount of matter. They try to give you the idea that mass is, where do they start with it? They say, what is an object? An object is what it's made out of. An object is made out of atoms. And this is a similar idea. They say, look, what is mass? Mass is the quantity of matter in an object. If you count the 10,000, let's say, hydrogen atoms, let's assume that's the unit of mass for the sake of argument. So we have 10,000 atoms in an object. So that's the mass of the object, 10,000 atoms. That's not the way they phrase it. They would say, oh, that's got 1 kilogram of mass, right? They wouldn't say it's 10,000 atoms. But why do they say that it's the quantity of matter? Why do they point to the 10,000 atoms? Because they say an object is that which is comprised of something. And so that's where they tie in mass with the object. You're supposed to think of mass as the object itself, as all those little components of the object. That's the issue. But what happens? A black hole crushes all matter out of existence. There you have 2 references, one from Professor Cole Miller, University of Maryland, the other one from David Harrison at the University of Toronto. And they both say that matter inside a black hole is crushed out of existence. So if mass is the quantity of matter and a black hole crushes all matter out of existence, we have a circular argument. Because a black hole is only made of mass. That's all it's got in it, essentially. And what is mass? It's the quantity of matter. And what happens inside a black hole? All matter is crushed out of existence. So what do we have? How can a black hole have mass if you just crushed all matter out of existence, and mass is the quantity of matter? So we have a circular argument. And that's the second problem I see with black hole. We have no definition. We don't know if it's an object or a concept. We don't know if it's a hole or if it's a ball, black ball or a hole. Black ball is a standalone three-dimensional object that floats out there in space. Hole is a little entrance into the fabric of space-time. I don't know how you can visualize that. That's going to be what I'm going to be talking about now. So these two things are different. And then you have the issue of mass, that they say, well, we're going to do it with mass, but mass is a concept. That's the first problem. Second, mass is really undefined. It's got 7 definitions because they could never define it. A couple gurus, John Wheeler among them, says that they don't have a definition yet of the word mass, nothing that they can really use. And then it turns out that, even if you define it as quantity of matter, we have a circular argument in that the black hole crushes all matter out of existence. If mass is the quantity of matter and it all gets crushed out of existence, how can you have mass? Which is supposedly what the black hole is going to use to affect stars from a distance. It's going to use its great mass. And I had a little fable that I created, The Elephant and the Turtle. Showed it the other day, but I'll show it one more time because it's pertinent at this point. And that's that, the elephant supposedly tells everyone that he can move the turtle around from a distance without touching it. And it does it with its mass. It doesn't do it with it doesn't do it with an elongated object. It does it with mass. And you say, well, how does they do it with mass? Mass is a concept. Well, it turns out that, the turtle figured out, because it could see in the ultraviolet range, that the elephant was using a stick to move him around, but the stick gave out ultraviolet light. And so, the elephants couldn't see it, but the turtle could. So the elephant was really cheating, was, giving turtles and everybody else a bunch of nonsense, a bunch of BS, that it could move objects from a distance simply because of its great mass. No such thing. You need to have a mechanism, a physical mechanism, an elongated mediator to do action at a distance. And what they want to do with the black hole is say, look, we're not going to do it with objects. We're just going to do it with this mathematical concept. We're going to take mass, right? And simply because we have lots of kilograms, that alone affects things at a distance. And this is nonsense. This is absolute nonsense. It's like saying that you're going to move a star around with love. And you say, well, what do you mean you do it with love? Yeah, see, because I have lots of love. I have tons of love. And the more love I have, the more influence I have over that star. Well, how did you do that? Well, the way I did it, see, love pushes the canvas, the fabric of space-time downwards, and creates this, depression. And the wall of the depression is curved, so the star wants to fall into the hole. So it's attracted to the hole. The black hole kind of pulls on it through this curved surface. That's what's happening. And that's what the black hole theory is all about, pulling it like that. What's the problem with that theory? Let's go with what's wrong with that. Here you have a three-dimensional object turning in space, and suddenly it turns into a two-dimensional object. You're going through the hole, and what are you going into? See, the question here is, what is the surface now? As soon as you get into the hole, what's the surface that's pointing towards you? What is in front of you right now? Do we have space? In other words, what's the hole facing there. See, we're not talking about a ball. We're talking about here, we're talking about a three-dimensional object that suddenly turns into a two-dimensional entrance to whatever. To whatever, because, you cannot conceptualize this because it's so realistic. Okay? Let me give you another vision of what I'm trying to say here. Here's another vision. Let's wait till it stops. I'll start it at the beginning. And it starts about here, right after this. Here you have a two-dimensional vision of a black hole. Okay? They turn it around, they turn it into a ball, just to show you that it's got an event horizon. Then it goes back to the two-dimensional ball, and they show you the balls falling in there. What's pulling those balls downwards? Why don't the balls fall upwards into a black hole? Why don't they show you this? Well, this would be counterintuitive. People say, well, why is it going up? Well, the reason balls go down is because on Earth here, things fall to the floor, and so they always like to talk about downwards. They never like to talk about things falling upwards because that's counterintuitive. So they have this show where they say, oh, the balls are falling downwards. And everybody says, okay, I understand that. There's a curved surface. Things fall downward. Well, here you have a curved surface. Why don't they fall upwards? Well, because gravity pulls it downwards. It's not the curvature of space that pulls things downwards, because the only way they would go downwards is if gravity pulls them downwards. Otherwise, if there's a curve, there's no reason for anything to follow that curve downwards. Okay? A curve can also go upwards if gravity is in that direction. What you got to identify is what gravity is, what is coming in contact with the little balls that are going upwards or downwards, like in the first case there. But the other issue, so we got two issues. One, they turn the two-dimensional hole, okay, which is that one there, and they turn it into a ball. They turn it into a ball because they need the event horizon. The event horizon is a sphere that encapsulates the singularity at the center of that ball. But then they turn this into a surrealistic scenario where they have the singularity at the bottom. That's where all the mass is concentrated, supposedly. And the mass, for whatever reason, pulls space-time downwards. The canvas of space-time, it's pulled downwards. Why is it pulled downwards? Well, because on Earth, we know that everything falls downwards. Nothing falls upwards, by gravity at least. And so what happens, because the excessive mass of a black hole pulls the canvas downwards, it creates a curve. And then they say, well, any object like a star or whatever that's near the curve just follows the curvature of space-time downwards. But it only goes downwards only if gravity pulls it downwards. Otherwise, there's no reason for that curvature to be upwards. If the source of gravity were upwards, then the curvature, would be in the upwards direction. The balls would fall upwards. Why don't they show this every day so that people would say, hold it, I got a problem. What do you mean the balls fall upwards? Yeah, because then you have to explain the source of gravity, and you can't just say mass. I thought mass pushed everything downwards. How come here I'm showing that mass is pushing it upwards? Okay, so this is the problem. The problem is that these people are trying to get away with first a 3D to 2D to 3D scenario. They go back and forth between the 2D and 3D. And second, they use the word mass, when mass has no physicality. Mass is a concept. You can't say mass does this or mass does that. You have to have a physical mechanism. Mass is a mathematical concept. So you cannot say that mass pushed the the canvas downwards, the fabric of space-time. It curved the fabric of space-time and created a depression. Okay, so you have to have something come in physical contact with a ball to explain gravity. You can't say that gravity does that because that's what we're trying to explain, gravity. You can't take gravity for granted and say, oh, I know what gravity is. Okay, so this is the issue. That's where the two of the problems are. The other issue that I want to talk about, I hope you understood that. I don't know if I should maybe clarify that one more time. You have the sheet, the what is it? The canvas of space-time. And unless you put any objects in there, it's a flat surface, supposedly flat. Now you put something in there, a star. Star has mass, meaning it's got some kind of weight. It's going to be affected by gravity. And so it pushes it downward, pushes the canvas downwards. What was two-dimensional suddenly becomes three-dimensional. Now you have some depth. Okay, you have a third dimension, which is height, okay, of the black hole in this case, right? The ball, the mass of that star, right, is so big that it becomes a black hole, and it just pushes the canvas of space-time so deep that any star, no matter how far away it is affected by it. And those that are very close to the hole are drawn in. Why are they drawn in? They're drawn in because of the geometry of space-time, the geometry of the depression. That's the argument that Einstein had in 1915, 1916. He says there's a curvature of space-time caused by the mass. But why does the mass push it downwards so that the ball can roll down the curve? We have to figure out how mass, a concept, bent space-time. Mass is not a physical object, it's a concept, so you can't say that mass did it. What's happening here is these people are saying, look, there was a star. It was so big, so humongous, had so much mass, that the mass is what bent space-time. First error. Second error is that they're invoking Newton. They're saying there's a force, it causes a force on space-time, pushing the depression downwards, downwards, so deep that it bends space-time. And now any object like a star, ball, just rolls down or tends to roll down this inclined plane, this curvature. Why doesn't it go upwards? Why doesn't mass push upwards and have the sun go upwards? You can't do that because you need to establish the source of the force that's bending the canvas, the fabric of space-time. You need to identify what elongated object is affecting the star. You can't say mass does it. You can't say mass bends space-time and that mass produces curvature and that mass compels the star to go around itself or to pull gases from its skin. You can't say any of those because mass is a concept. You have to identify the physical object that's pushing the canvas downwards, that's causing the curvature of the depression, the canvas being curved, of the geometry of space-time being modified. And then, yes, you could explain why this ball falls into the hole. And again, since there's no direction in space out there, why doesn't it go upwards or into your eye or away from your eye? Why doesn't it do it sideways? I got a little GIF to show you this. It's my fish tank analogy, okay? Here you have a fish tank. And we're going to fill it up with water, okay? and we're going to turn it into space because that's a three-dimensional volume there. And space is more or less, you got to think of it as three-dimensional volume. What these people are doing, they're putting black holes in there, and the black holes are sucking in matter and going down deep into that cone. But you can see how surrealistic this is because they have a flat top. Each one of these black holes, if you look at them, they have a flat top. And the question is, which way is the flat top facing? You have one facing downwards, the other one facing upwards, the other one facing towards the side. What is that hole into? This is a surrealistic scenario when you put a black hole, a two-dimensional scenario, onto a three-dimensional volume. That's the problem. The problem is that these people are introducing here. Let me show you the black hole in a little bigger so that you can see. Here's the black hole. You can see it's got a flat top. They're putting that into that background, which is supposed to be a three-dimensional volume. So they have a two-dimensional flat surface with a hole into it, right? And they're putting this in a three-dimensional volume, which is the volume of space. You could even take one more step and say, look, it's a four-dimensional space-time. So we got a two-dimensional flat surface in a four-dimensional volume, if you can picture that at all. So what's the problem? The problem is that, these people are cheating. They're saying, look, we have this black hole, and it's got a flat entrance because a hole can only be into a flat surface. Like, I just showed you Bugs Bunny here. See if I can find him again. Was it this one? I think it's this one. No, wrong one. I'll get it here. Give me a second here. Is it this one? No, same one. No, wrong one. Well, I can't find it now. I don't got so many of these. Is it this one? No, this is JFG's. Unbelievable how I can lose these things. No, wrong one. I'm going to have to try them all until I get the right one. Here it is. Okay. See, you can see the difference between a black hole and between a hole and a ball, and between a black hole, which is supposed to be a two-dimensional entrance, surrealistic entrance into space-time, because that's the one on the right. If you see the one on the right, on the bottom right, it's a hole, and it's treating space-time as a flat surface, as if you were at the edge of space-time. Okay? It's if you were at the surface of space-time, not as if you're inside the volume of space-time. So the reason you can see the hole is because there's nothing on this side of that surface. It's like you're outside of space-time looking at a hole like you would look at a hole in a Swiss cheese. You can see the hole. Why? Because you're on the outside looking at the cheese, and you're looking at a hole going inside the cheese because there's nothing on this side of the cheese. How do you see a hole inside the cheese? Which is what they're trying to illustrate. And that's what I'm showing here with a fish tank analogy. I'm saying, here we have a volume of water, and that's going to turn into the volume of space, okay? And they put a black hole in there, a cone, a two-dimensional cone, and the surface of that hole is into the volume. I mean, I can understand if the hole is at the edge of the surface of, the surface of space-time. You cannot imagine that if it's inside the volume. That's the problem with this scenario. But it doesn't stop there. There's another problem also with it, and it's like this here. Turns out that gravitational waves coming out of a black hole, they're transverse waves. Gravitational waves are transverse waves, but they are not dipole transverse waves like most electromagnetic waves. They are quadrupole waves. They simultaneously squeeze and stretch matter in two perpendicular directions. So there's a picture of it. You see that the wave is changing its shape. It's squeezed first in one direction, then it's squeezed in the other direction. Okay, that's all they're saying. But the important part here is that gravitational waves are transverse waves. Keep that in mind. Transverse waves is like the famous transverse wave of light that they show you in high school. That's what a transverse wave is. Transverse wave means that the wave moves up and down perpendicular to the direction of travel of the wave as a whole. That's what a transverse wave is. Okay, and so what's the problem? The problem is what I showed here earlier. I think it's this one. Look at the waves that this, again, you're looking at the surface of space-time there, so the holes are into space-time. What's the black stuff on top of that gives shape to that surface? That's the first problem, okay? But now look at the waves. The waves that are coming out of there, those are transverse waves. They're ocean-type waves. And ocean-type waves really are a mixture of longitudinal and transverse waves. They've got both of these. Okay? But see, ocean waves are surface waves. Again, keep in mind they're surface waves. And what these people are saying is that, these surface waves are coming out of the volume, the inside volume of space-time. They're not coming out of the surface of space-time. They're coming out of the inside of the ocean, not at the surface of the ocean. And that's also the problem with what Peter scenario had. He had a surf, and that's what I was trying to tell him in the other day. I don't think he understood what I was saying to him. He's got a surface, and he's talking about what's happening to the little oil drop here. Let me put it up there so we have something to look at. He's saying, look, here we have it. We have the surface of the oil. This is not the inside of the oil, it's on the surface. And you can only create these transverse / longitudinal waves because both components are in those waves. You can only create them on the surface of the oil. Okay, you can't create this same effect inside the volume of the oil. You can't create it inside like I'm showing here with the, where was it, the tank, the fish tank, if I can find it. You can't do it here inside the volume of the fish tank. You can do it on the surface of the fish tank. You can't create waves on the inside of the, you can't create transverse waves on the inside of the tank. Why? Because transverse waves only propagate in solids. You have to turn space-time into a solid, okay? And here you have it. The particles in transverse waves move perpendicularly to the direction of propagation, so it cannot propagate in a gas or a liquid. Blah, 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 blah. You can read the rest of that. Transverse wave need a rigid medium. Okay, you can't do it in water. You have to do it in solids like steel. That's why I had that statement from this fella who said, that, where is it? That space-time is billions and billions and billions, space, he was saying, billions and billions and billions times stiffer than steel. Makes no sense whatsoever. These people have turned space not only into a physical object, but into an object that is stiffer than steel. And you wonder, how do the poor astronauts manage to get through the steel in there? Imagine if all of space or a solid bar of steel? How does the astronaut go out there and not even get his, elbow scratched with all this steel? That's the issue. These people are totally irrational. They're idiots. They're idiots. They've turned space into a physical object and into a an object that's stiffer than steel. And they had to do that for the transverse waves. So when these people from LIGO say that they detected waves, okay, from the collision of two black holes, I don't know how they collided through all that steel, but let's assume they collided. The waves that this thing generated, this collision generated, those waves are transverse waves. Transverse waves can only propagate in steel, in solids. They cannot transfer through water, liquid, they cannot transfer through gases. And so these people had to take the next step and assume that space is a physical object, not only a physical object made of particles, as we know from quantum, but it's stronger than steel, stiffer than steel, because that's the only way you can transfer transverse waves all the way to Earth and detect them. And so what's the problem with Peter's scenario? Well, Peter's scenario is that he's got these, he uses it in an analogy for stuff in quantum, right? And let's see if I can find this again. He uses it here to show his water droplet, but that's a surface phenomenon, first. Second, he's doing it in liquid. He can't simulate anything related to quantum because quantum works with transverse waves. Transverse waves only propagate in solids. And second, you got to show this scenario not at the surface. That's easy. Show me that same thing inside the volume of the oil first. And second, how can you do it in oil if it's going to create, if it's supposed to create transverse waves, and transverse waves can only be propagated through solid objects? So he's got too many problems with this scenario. This scenario is worthless. It's a nice experiment. People like to watch fancy things, saying, hey, let me show you something, some fancy stuff. Look, I can show you how these drops bounce and go around, and they love to watch all these things. They're fascinated by all these experiments. But what they'll never be able to do is explain the cause, the mechanism. That's when they describe it mathematically. They say, look, the wave does this, and there's this potential, and we have a probability distribution, and blah, 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 blah. And never will they tell you, let me tell you what the mechanism, let me tell you how Mother Nature does this thing, what the magic is. They'll never be able to tell you that. And they never even touch the subject because they always think that a description is the same thing as an explanation. They think that the description is a mechanism. And they say, yeah, I've explained it. I've told you the mechanism. See, here's the equation. That's what they tell you. So if you're waiting for an explanation, if you're waiting to understand the mechanism, well, you got a long wait. Believe me, you'll be traveling through time. Okay, so here's another statement, this one from the Stack Exchange, that transverse waves are shear waves whose particles move perpendicular to their direction of propagation. That's known as a transverse wave, right? They can propagate through solids. Solids should be there, huh? Because solids have enough shear strength. The shear strength is one of the forces that hold a solid together and prevent it from falling apart. That doesn't happen in liquids. The case with liquids is that liquids do not have that much shear strength. For example, consider this. If you take a glass of water and suddenly somehow you remove the glass, the water will not keep its shape and will just flow away. So in fact, it just boils down to the fact that transverse waves need a medium rigid enough to propagate, which liquids can't provide. So you cannot use liquids to do anything in quantum. Anything, because quantum deals with transverse waves at the invisible level, at the subatomic level. It's all transverse waves. So if you cannot produce transverse waves because you put liquid in there, you say, well, there's this fluid, ether, whatever, that's flowing. No. It's got to be rigid like a piece of stone. Then you can, or steel, right? Then you can talk about transverse waves. Then you can make your case. But then that means the atom is trapped in a box of steel. And I was trying to tell that to Peter the other day that, you know, he's taking this 2D scenario, but when we talk about the atom and anything going around the atom, we're talking about a volume. We're talking about a 3D scenario. So how does he extrapolate his 2D analogy to the 3D scenario? He can't, and he never will, because it's surrealistic. It's it's nonsense to say that you can put a 2D black hole into a 3D universe, 3D space. And that's when they slightly, they have this sleight of hand. They say, look, I'm going to put the ball in the volume. I'm going to put the ball in space, but let me explain it to you, what it does. Well, what the ball does is curve space-time. What do you mean it curves space-time? Yeah, it curves space-time and all the things fall into the hole. What do you mean, no? Where, in what direction is the hole? Let me show you. And they point to the 2D scenario now. They suddenly switch on you and go to the two-dimensional scenario, and they show you, the curve. And they say, see, the depression is caused by mass. And the star, this ball, this whatever over here falls inside the hole. So they keep going into from 2D to 3D to 2D. If they talk about, if they're going to talk about the event horizon, they have to put a ball in there. They have to put a 3D ball in space, right? So here's this black ball in black space, right? And they say, well, here's this ball, and this is what this massive star became, a ball. But then you can't understand why it's attracting things. They say, well, what it does, the ball weighs down space-time. And now they go to the 2D scenario and they show you the curvature of space-time. They say, see, the sun falls inside the hole. What hole? The hole created by the ball that pressed down on space-time. And it turns out there is no ball to begin with. It's just a singularity which is zero-dimensional. Lots of mass, no body, no structure, no matter. What is mass? It's the quantity of matter. It's been crushed out of existence. We have nothing. That nothing curves space-time. It did it downwards. It didn't do upwards. Why did it do it downwards? Because it needed Newtonian gravity. Force, the word force, no longer the curvature of space-time, but force. So it's all a mess. The whole thing is irrational, is nonsense. I hope you followed through, because there's many aspects to this, okay? Anyways, we're about at the end of time. I've got a couple more things here. The first one is that you got to distinguish between wave and current. Okay, wave is up and down movement on the surface of the water. It's a 2D scenario. Current is what moves through the body of the ocean. Okay, it's the movement of water under the ocean. It's underwater currents. That's what a current is. And here I have a little picture of it so that people understand the difference between waves and currents and should not mix them. Wave is what's on the surface of an ocean. Current is what goes on where the fishies are, right underneath, is somewhere in the body of the ocean. So you should not confuse current with waves. If you're going to talk about the scenario of a black hole being a three-dimensional ball inside the volume of space, three-dimensional space or four-dimensional space-time, whichever, you have to talk about currents and not about waves. Certainly you cannot talk about transverse waves if space or space-time is a fluid or a gas. Space or space-time have to be made of steel or stronger than steel. They have to be made of a single piece almost, right? They have to be stronger than steel, stiffer than steel in order to convey or propagate transverse waves. Okay, that's why they had to make it, that's why they talk about space being billions of times stiffer than steel. And here I have another difference for just so you know the difference between longitudinal and transverse waves. Earthquakes, they produce both through the earth. And the funny part is that longitudinal waves travel 1.7 times faster than sheer transverse waves. And so, again, the analogy that I've got is that if this is the case, that longitudinal waves travel faster, if this is the case, then if you extrapolate this, that means you should hear the thunder before you see the lightning flash. In other words, sound should travel faster than light if light is comprised of transverse waves, because longitudinal waves, such as sound, travel faster than transverse waves. So you can't say that light is a transverse wave or that anything in quantum mechanics is a transverse wave, because it would be as slow as hell. And that takes me to my last GIF there, which I've shown in the past, but I'll put it one more time for those newbies. You can see that the transverse wave is a snail, goes very slowly. Turtle beats the hell out of it, 1.7 times faster. Turtle is the longitudinal waves, like sound. And the cheetah is the torsion wave. It's mediated by what? It's mediated by a rope. Torsion on a rope, that kind of wave, that disturbance, travels millions of times faster than a longitudinal wave, which travels faster than a transverse wave. So light or gravity, if they're made out of transverse waves, they should be as slow as, you should beat them by running. Anybody can beat a transverse wave. It's easy. They're slow. So you can't use transverse waves for anything in quantum, and especially to simulate light or gravity. And with that, we end the show today. So those were the problems with the black hole ideas and the surface waves that were presented the other day, both by JFG that showed this 2D scenario and the whole, pointing upwards, but they never identified the medium that's upwards here. Why? Because that should be the surface of space-time. That's the end of space-time. That's where space-time ends. You're at the surface of space-time. Then you can see the whole. And then the question is, well, what's on that side? What's on the other side of the Swiss cheese? I can see the Swiss cheese. On this side, I got air. That's in the case of the Swiss cheese. Okay, now let's look at space-time. Space-time has a hole in it at the surface. What's on this side of it? You see, you can't introduce that scenario in the middle, in the volume of space-time. You can only do it at the surface. Those are the arguments. So keep that in mind whenever you discuss against a mathematical physicist. We'll see you next time on Sunday, and hopefully I can get back to where I was on the point, and I'm going to continue with that next time, unless, I might do a recap of what I said today, so keep that in mind. We'll see you then next Sunday. Bye-bye.